Welcome to The Explainer. Today, we're investigating a pretty fascinating technological whodunit, sourced straight from Chapter 12 of the book AI-Powered Search. Imagine you've built a machine learning model, right? A true prodigy. In the lab, it gets straight A's. It perfectly predicts what users want based on all your historical data. But the moment you actually release it into the real world, it completely bombs. Well, today, we're going to uncover exactly why that happens and how modern search engines fix it.
Okay, let's dive into this. What actually happens when a flawless, highly trained AI search algorithm fails its real-world exam? Actually, it's not a glitch in the code at all. It's a fundamental flaw in the way automated learning-to-rank, or LTR systems learn. We're going to essentially perform an autopsy on a failed algorithm today to really understand the hidden biases shaping the tech we use every single day.
The ultimate culprit behind our mystery is something called presentation bias. You can think of this as a massive algorithmic chicken and egg problem. In an automated learning-to-rank system, the AI learns from what users click on. But here's the catch. It can only learn from the results it actually presents to the user. If the truly relevant result is buried on page 10, the user never sees it, never clicks it, and the AI literally never learns it's relevant.
Section 1. Reality check. A/B testing.
To really catch presentation bias in action, developers have to take their AI out of the simulated lab environment. Because look, you can run offline simulations all day long, and your model might boast flawless theoretical performance because it perfectly memorized past user behavior. But out in the real world, you absolutely need an A/B test. An A/B test randomly assigns live users to different ranking models, just to see which one actually drives business outcomes, like real purchases on an e-commerce site. The real world is always the ultimate validator.
And here's the shocking twist from our source material. The developers ran an A/B test for the search query Transformers DVD. They pitted their newly trained so-called golden student model against an older, seemingly dumber baseline model. Get this, the golden student secured only 15 purchases. The old baseline model, it got 21. That highly advanced model performed objectively worse in the real world. Crazy, right?
Section 2. The search, chicken and egg.
Now, what's really interesting about this slide is exactly why our golden student failed. It all comes down to a fundamental limitation. Human users are entirely restricted by the interface directly in front of them. The AI might have 1 million products in its database, but if you're looking at a phone screen, you're only interacting with the top 3 or 4 results. Users literally cannot give the search engine positive feedback on a great product if the engine never shows it to them in the first place.
And this traps the search engine in a vicious, self-reinforcing bubble of bad data. Let's just walk through this negative feedback loop step by step. First, an initially untuned model returns mediocre search results. Second, the user, just wanting to find something close to what they need, is forced to click on the best of those mediocre results. Third, the model sees that click and falsely assumes, aha, this mediocre result is highly relevant. And finally, the truly desired items remain completely hidden forever. It essentially starves the model of the good data it desperately needs.
Section 3. To explore or exploit.
So how in the world do we break an AI out of its echo chamber? We basically face the core dilemma of machine learning, the explore versus exploit trade-off. On one hand, we can exploit. This means optimizing for what the model currently knows performs well, safely aligning with existing training data. On the other hand, we can exploit. This means taking a risk on unseen, unproven results to gather new knowledge. Think of it like a self-driving car. If it only exploits the one route it knows, sure, it gets you home safely, but it never learns if a much faster route exists. To find a better way, it occasionally just has to explore its blind spots.
Section 4. Finding blind spots systematically. Now, we obviously can't just throw completely random, terrible search results at a user. That would ruin the experience. Instead, developers use clever mathematical tools like the Gaussian process. And this brilliantly illustrates how the system figures out exactly how far it can stretch its current knowledge before it's just blindly guessing. It's a method built specifically to safely navigate that uncertainty.
The source text actually uses a fantastic metaphor for this: river depth. Imagine you know the exact depth of a river at 2 specific points, because past expeditions measured them. You can make a highly educated guess about the depth right next to those points. But the further you step away from those known safe measurements, the more your uncertainty grows. The Gaussian process maps out this exact uncertainty, so the AI knows exactly where its knowledge is strong and where its blind spots are.
As the source text states, Gaussian processes use incomplete information to make careful trade-offs in the likely quality and the knowledge gained. In practice, developers use an algorithm here called expected improvement. It systematically looks at those blind spots we talked about and carefully selects new, unexplored search results for users to interact with. It calculates whether the risk of showing an untested item is actually worth the potential reward of learning something entirely new about what the user wants.
Section 5. The active learning loop.
By integrating this calculated risk-taking, we completely evolve from a static model into an active learning system. When developers deployed this new model, one that dynamically balances exploring and exploiting, they ran another A/B test, and the results were completely triumphant. For that same Transformers DVD query, the old baseline got 21 purchases. The new active learning model, 145 purchases. By systematically gathering new signals and exploring beyond its initial training data, the new model completely blew the old baseline out of the water.
So, the crucial point is this overarching system architecture right here, the finalized end-to-end automated LTR loop. It's a continuous 5-step engine. 1. You exploit your known knowledge to give users good results. 2. You strategically explore blind spots to find potentially better results. 3. You gather the new user click signals from those exact explorations. 4. You rinse out the old biases. And 5. You repeat the whole cycle to constantly retrain the model.
It really is a brilliant solution to a deeply hidden problem. The next time you're shopping online or just researching a topic, ask yourself, how might presentation bias be hiding the absolute best results from you? Are you really seeing the whole picture, or just the echo chamber the algorithm built for you? Definitely keep that in mind as you navigate the digital world. Thank you for joining me for this explainer, and as always, keep learning.